Hello students, we are going to look at topic 3 on gaseous states. So this is the third topic you will encounter in your JC1 studies. We will going to look at some of these learning objectives in details in the lecture series. So you can find them in your syllabus documents from 3A all the way to 3D. Some of it you will find familiar from what you have learned in secondary school physics. For example, the relationship between pressure and volume, and probably the relationship between volume and temperature. Yeah, you would have encountered them, otherwise known as Boyle's law and Charles' law. So it's not too difficult, I hope, except that I think in most cases students find a little difficult to combine them together, making use of PV equals to nRT, and then to sketch the graph, and at the same time make some careless mistake in terms of calculation because they remember the units wrongly. Yeah, actually there isn't really a real need to remember the units, but I mean, if you wish to derive it from the fundamental principle, I think it helps a lot for your understanding. Yeah. Other than that, gaseous states for H2 chemistry is just a small topic. Not to say it's not important. It's important it cuts across all areas of chemistry which you will encounter in H2. Especially in the calculation. So even in organic chemistry or inorganic chemistry, we can ask you to assume ideal gas behavior, and then from the information given, supposed to calculate out a value for the MR. Yeah, so it can be tested, but you just need to be a little bit careful when you are attempting the calculations. Okay, so we have the first section on gases, which is through the development of mole concept from the experiments. So you might want to read through it on your own and take note of some of these very famous chemists. For example, Robert Boyle related or developed the Boyle's law, and then Jacobs Charles, and then Gay-Lussac, and then they kind of like come together. They don't really come together, but they develop the principles separately, and then later on people put them together and then combine into one, what we call the ideal gas equation. So the ideal gas equation, if you move on to university level, you will learn other forms of ideal gas equation when they actually include some correction factor to make the equation more accurate. But I think in H2 Chem you don't really encounter those added equations. If you are required to know them, or you are required to perform some applications kind of questions, then I think the question itself will guide you through, so not to worry. Yeah. If you are interested, you can read more, especially from those introductory chemistry book where when you go through a typical course in university chemistry, you will be introduced to some of these ideas again. But if you want more in-depth treatment, you might want to look at physical chemistry text, because they really explain all these things in much greater details. Okay, other than that, I think we'll just jump straight in. So I think the first thing we need to understand is Avogadro's law, which is important for you to understand and derive future relationships. So of course, it reads equal volumes of all gases under the same temperature and pressure contains the same number of particles. Okay, and then in these two learning objectives, which you will be familiar from secondary school, it's 1 mole. So 1 mole is defined exactly as 6.02 times 10 to the power of 23. Of course, there is a more accurate one, which is 6.023, which you might have read before, but for H2, I think we'll leave it as it is. Take note of the Avogadro constant is represented by L. So if you go to the data booklets, you will see that Avogadro constant is written here. Is the third constant given to you in the important values, constants and standards. So it's represented with L. The exact value given for H2 is 6.02 times 10 to the power 23. So do not use 6.023 times 10 to the power 23. Alright. So if you use this, then your values will be a little bit off in your calculations. Okay, and the unit is mol. Okay, do take note of it. It's not mols. So even if it's plural, please do not write it as mols. Okay, so you will still write it as mol, but you will pronounce with an s at the back. So you say 1 mole and 2 moles. Okay, but the units will be the same. Just as like 1 meter, 2 meters. For meter, you do not add an s at the back. Okay, short form is represented by this particular Greek letter is known as eta. So it's written like this. So just a stroke down and then a curve, a tail at the end. Okay, so this eta it can be represented as number of moles of blah blah blah. So let's say number of moles of argon atom. So I can just write it as AR with a subscript equals to let's say blah over blah. Okay, so this is how you can use the Greek letter eta to represent amounts or number of moles. Relative molecular mass again is defined as average mass of one molecule of a substance, or it could be one molecule, or it could be one atom for monoatomic gases. Okay, divide by 1/12 the mass of one atom of carbon-12, which means the reference unit here is 1/12 the mass of carbon-12. So carbon-12 is taken to be 12 atomic mass units. So in this case, because it can be measured quite accurately to the 4th decimal place as 12.0000. So carbon is taken to be the standards. Okay, yeah. So some of the bullet points here you need to take note of. Because of the presence of isotopes, we normally use the word average. Okay, is necessary in the definition. Do take note of it. So it's not exact value. Okay. Yeah, other than that, I think the rest are fine. Okay, so let's move to 1.2, which is the units of pressure. So pressure is defined as the force exerted per unit area. You will have learned it in secondary school physics. If you can't remember, it's fine. Just read a little bit more about it. Okay, so traditionally, it's being measured using mercury. Yeah, so some of you might be a little bit familiar with this if you read a bit into history. So atmospheric pressure is defined as 760 millimeters mercury. So it's the height where the atmospheric pressure will exert onto mercury, and then how mercury will be lifted, or due to the difference in pressure, it will be forced up in this tube. Okay, so this is a traditional unit. So normally we do not use a mercury barometer now. So you can just forget about it if you want to. Yeah. Okay, so right now the SI unit for pressure is Pascal. So defined as 1 Newton per square meter. I think for H2 chem, the Pascal is more common as compared to using 1 Newton per square meter. Okay, so you might want to take note of it if you wish to lah. I think it's good to know both. So just know that 1 Pascal is equals to 1 Newton per square meter. Okay, so very commonly used in A levels. Okay, so it's a much smaller unit as compared to atmospheric pressure. So there is a need for you to learn how to convert them. So you need to know that 1 atmosphere is exactly 101325 Pascal. Yep, so if you look at history, this is also equals to 760 millimeters of mercury height. Okay, you notice that 1 bar is very close to atmospheric pressure. Okay, it's 10 to the power of 5 Pascal. Yeah, but when we write out the units, it's a little bit, the values are a bit different. Yeah. So now a lot of standards are defined using bars rather than atmosphere. Yeah, but it's important for you to know the exact values for one atmosphere. It's given in your data booklet as well over the third, 9, 10, 11, the 10th molar volume of gases. So you take note that RTP is expressed as 101325 Pascal 1 atmosphere. So there isn't a need for you to memorize because it's given to you. Okay, and then later on below there is a measuring standards for gas samples. So you are supposed to know, let me just put it categorically, you're supposed to know two standards. One is standard temperature and pressure. Do take note of the spelling. Standard, okay, temperature and pressure. So this is referring to 0 degrees Celsius and 1 bar. Okay, and molar volume is defined as 22.7 dm cube per mole. There is also another standard you need to know, which is room temperature and pressure, short form RTP, defined as 293 Kelvin or 20 degrees Celsius. Take note, this is not 25 degrees Celsius. Okay, so do take note of this. Many students get confused. Okay, might be a bit different from what you learn in secondary school, but it's good to take note of it. Pressure is 1 atmosphere or 101,325 Pascal. Okay, it's not 1 bar. That's the difference. And then molar volume 24 dm cube per mole. Okay, so it's defined for you. Data booklet also has this value, so you don't need to memorize them. So honestly, if you do enough question, you will have remembered it. But if not, just flip to the second page of your data booklet and all the datas are given to you. Yeah, so there isn't a need to memorize them. Just take note of it. Okay, yeah. So we'll move on to section 2, simple gas laws and ideal gas law. So basically we want to relate 4 macroscopic properties: pressure, volume, temperature, and amount in number of moles. Okay, so so for a simple gas law, for example, in this case the Boyle's law, which you have learned in secondary school, right? You learned that the volume of a fixed mass of gas is inversely proportional, okay, to its pressure. So that means that volume is inversely proportional to pressure in this case. So that means that as volume goes up, pressure goes down. Okay, so I think mathematically we write it as volume inversely proportional to pressure. Okay, in this fashion, or you can just switch them over. Yeah, so if you recall from your mathematics, there is also a proportionality constant which you can introduce. So if volume is inversely, sorry, I think I wrote this wrongly. So if volume is inversely proportional to pressure, so therefore volume is actually equals to a constant. That's called C over P. Okay, so C is actually a constant, which is a real number lah. So it's a constant here. Okay, so for graphical representation, I do believe you will have learned them in Sec 2 or Sec 3, right? How do you plot P against V? Yeah, so for inverse proportional relationship, I mean, what you can do is you can just look at it like if let's say volume approaches infinity, then you know that pressure approaches 0. Yeah, so over here you know that at very high volume this is close to 0, but it will not hit 0. Yeah, so there will be an asymptote. So yeah, so it's the same logic. As volume approaches 0, pressure will approach infinity. Yeah, so you will get a very large value. So you will get somewhere here. So if you connect these two parts, you will get a curve that is like this. Yeah, so I don't think this is something which you are not familiar with. Okay, you can also plot P against 1 over V, or we call it P against reciprocal volume. So you get a straight line which passes through the origin. Okay, and next we have Charles' law, which it was mentioned that at constant pressure. Okay, earlier on I think I forgot to mention that for Boyle's law, the temperature is a constant. Yes. Yeah. Okay, so for Charles' law, the pressure is a constant, so the volume is directly proportional to the absolute temperature. So this is very important. This is what we call thermodynamic temperature. Okay, so absolute temperature is also known as thermodynamic temperature. Okay, so the mathematical relationship, because it's directly proportional, so therefore you can also write it as V is equals to constant Ct. Okay, so if you plot V directly against T, take note that this is thermodynamic temperature, so you get a straight line which passes through the origin. Okay, so the origin is over here. Yeah, but if you are plotting V against temperature in terms of degrees Celsius, then you will have to ensure that your graph cuts V equals 0 at minus 273 degrees Celsius. Yeah, so this is very important. So there's a sort of like a shift in the graph. Yeah, the reason is the conversion between degrees Celsius and thermodynamic temperature. Okay, so temperature in degrees Celsius is 273 plus, oh sorry, it's the other way around. Temperature in Kelvin is temperature in degrees Celsius plus 273. Okay, so do take note of this. Yep. Okay, moving on to the next part. Okay, so at constant temperature and pressure, I think earlier on we have seen this is what we call the Avogadro's law. So the volume is directly proportional to the amount. Okay, number of moles. Yep. So if you plot them, you'll get a straight line which passes through the origin. Okay. So therefore, for constant temperature and volume, pressure of a gas is directly proportional to the number of moles present. Okay, with that, we can look at exercise 2.1. Okay, so the question is, which of the simple gas laws is at work in each of the following examples? So for part 1, the bubbles exhaled by a scuba diver grow in size as the bubbles approaches the surface of the ocean. So over here we have to assume that the temperature is a constant, although it's a poor assumption. So in that case, we are likely to apply Boyle's law, because pressure is inversely proportional to volume, or you can view it as volume is inversely proportional to pressure. Okay, so the pressure exerted by the water decreases as the depth of water decreases. Yep, so therefore as it rises to the surface, due to a lower in pressure, the volume of the bubbles increases in size. Okay, then for part 2 on collision, airbags in cars inflate rapidly. So a sensor triggers the injection of sodium nitrite according to the following equation. Yeah, so you realize that at the beginning we do not have any gaseous molecules, we only have solids. Yeah, but as the reaction proceeds to completion, we have 3 moles of N2 produced per 2 moles of sodium nitrite. So if you reduce it to per mole of sodium nitrite, so there's an increase in 1.5 moles of nitrogen gas. So in that case, you expect an increase in volume because we are applying Avogadro's law here. Yeah, so volume is proportional to the number of moles of gaseous particles. So V is directly proportional to N. For part 3, the print head of a bubble jet printer contains 64 or 128 tiny nozzles. And then the tip of the nozzle is filled with ink, which is then heated by an electronic heater. So this vaporizes the ink, and a bubble of vapor ink is then published on the paper. So this bubble, when published, acts as a dot or a letter or image. Okay, so what are we looking at here? So you do take note that there are some terms which you can look at it. It includes being heated up, so there's a temperature component, and then a bubble of the vapor ink published. Yeah, so we are probably looking at the relationship between volume and temperature. So in this case, we are looking at Charles' law, where volume of the ink is directly proportional to the temperature. Okay, then moving on to section 2.2 with what we call the ideal gas equation. This is probably the most important equation you need for H2 Chem. Yeah, famously recited as PV is equals to nRT. Yeah, after you rearrange the expression together. So PV equals to nRT is something which you need to remember because it's not in your data booklet. Yeah, so do take note. It expresses the relationship amongst the four variables, PV, T, and N for an ideal gas. Okay, so ideal gas is one which follows this equation exactly under all conditions of pressure, volume, and temperature. Yeah, so this is a very important relationship which you need to remember, so do take note of it. Okay, next we'll be using the ideal gas equation in calculation. So we are able to use the ideal gas equation to determine the four variables mentioned above over here. So we can use it to measure pressure if you are given a rest, amount in terms of number of moles when you are given a rest, so on and so forth. Okay, take note that R is given to be 8.31 joules per mole per Kelvin is actually given in your data booklets over here. Okay, some of you might be wondering how come there's a joules out from nowhere. So over here I'm just going to show you a very simple derivation. Okay, so over here we will use the condition of room temperature and pressure. Okay, so that will be 101,325 Pascal, and then temperature will be 293 Kelvin. The molar volume will be 24 dm cubed. Okay, so we'll just use it here. So over here we have PV is equals to nRT. So we'll attempt to calculate R, which is equals to PV over NT. Okay, so you know that the pressure is given to be 101,325. The volume is 24 dm cubed. However, the volume when we are applying ideal gas equation has to be in cubic meter, so we need to factor it in. So that will be multiplied by 10 to the power of -3 to convert it to cubic meter. And of course N over here will be 1.0, and then temperature will be 293 kelvins. Okay, so if you just punch the calculator, you will get a value very close to 8.31, although it's not exactly 8.31, it's actually 8.299658703 lah. Yeah, so some of you might be wondering why is that the case. Of course you should know that the conversion for the temperature to the thermodynamic temperature is not exact, and then there are some of these factors you need to consider. Yeah, but most importantly, you might be wondering what about the units for this. Okay, so if you scrutinize this whole derivation, right? Okay, so let's try. Pressure is in Pascal. Okay, then volume is in cubic meter. Okay, and then amount is in moles with moles, and then thermodynamic temperature is in Kelvin. Okay, so over here I think you can see quite clearly that moles and Kelvin actually appears, and they are the reciprocal, so I think that's fine. But why is it that Pascal multiplied by cubic meter is joules? So some of you might be wondering. So we need to go back to our fundamental definition. What exactly is pressure? So pressure is the force applied per unit area. So force in this case is in newtons. So if we convert this to Newton per square meter, so that's meter to the power of -2, then multiply it by cubic meter. So we are going to get a Newton meter. Newton meter is not a very inspiring unit, because if you don't really do physics, you might not exactly know what this is equals to. Yes, this actually equals to joules. Okay, yeah, because this is actually the energy transferred to an object. Okay, so when a force of 1 Newton move the object in the direction of the force by 1 meter. Okay, so basically we have an object here. So and then after that you push it 1 meter. So the object is here. So this is 1 meter. And then you apply a force. So you apply a force of 1 Newton. Yeah, so this is defined as the joules. Yeah, so if you put this in, Pascal multiplied by cubic meter is actually joules. Yeah, so the units here, joules per mole per Kelvin, is actually correct. I'm not trying to dispute whether is it correct or wrong, but just trying to showcase to you what you have learned. You know, it's in the correct direction, and these are some of the things which I thought if you learn them in a more complete manner, you'll be more interested in, and you'll have a greater and more holistic understanding. Okay, so moving on to the next part, we have exercise 2.2. So you were told that on the surface of Venus, the temperature is 470 degrees Celsius, pressure is 1 atmosphere. Okay, a very good habit here is straight away converts to the SI units required when you want to apply ideal gas equation. Yeah, so don't just keep that as degrees Celsius. Okay, so please do the conversion. So add 273 to this 470, you will get 743 kelvins. Okay, so 1 atmosphere, you know that is 101325 Pascal. Okay, so what is the volume occupied by 1 mole of the ideal gas under this condition? So basically, just sub into the ideal gas equation. So we have PV is equals to nRT. Okay, so we want the volume. So in this case, the volume is equals to nRT over P. Okay, so N is 1 because you are given 1 mole, and then R is 8.31. Temperature is 743 Kelvin, so 743 Kelvin. Divide by the pressure, which is 101325. Okay, so over here you will get the volume in cubic meter, so you should be getting 0.0609 cubic meter. Okay, so you should be able to perform this calculation quite easily. You can keep it in cubic meter, or if you wish to, you can convert it to dm cube, so that would be 60.9 dm cube. I think this looks like a more reasonable number. Yeah. Okay, then you can use the ideal gas equation to determine the MR as well. My suggestion is there isn't a need for you to memorize this. If you wish to, you can, but you don't need to because you can always derive it. Okay, so for example, in exercise 2.3, in a strange experiment, 0.1 gram of a gas, take note of the mass, okay, is found to occupy 83.1 cubic centimeters. So again, you need to convert this to cubic meter. So just make sure that you multiply by the correct units. So 10 to the power minus 6. Yeah. So again, for those of you who have issues converting, you can always use this method, which I learned from my primary school teacher. Yeah. So you just assume a cube 1 cm by 1 cm by 1 cm. If you want to convert to cubic meter, you just ask yourself the question, how do I convert cm to meter? So you just multiply by 10 to the power minus 2 meter. So therefore 1 cubic centimeters is actually equals to 10 to the power of minus 6 cubic meter. Okay, so over here you are told STP, standard temperature and pressure. So you should know the values. In case you forget, just go back to your data booklets. Okay, so these are the values given. STP 10 to the power of 5 Pascal, 273 Kelvin. Okay, so yep. So next, let's try to perform some calculation. So again, you can just go back to PV is equals to nRT over here. So again, the pressure is 1 bar, so that's 10 to the power of 5. Okay. And the volume here is found to be 83.1 cubic centimeters. So again, we convert to cubic meter. Okay, the number of moles we are not sure because we are not told, but you know that number of moles is actually equals to the mass divided by the MR. So we can just plug it in over here. And then ideal gas constant 8.31, thermodynamic temperature in this case it's STP condition, so that will be 273. So again, you solve for MR. So if you just punch your calculator very quickly, you should be able to get 27.3. Okay, yeah. Please take note of what you are asked to calculate. Okay, so because some question asks you to calculate relative molecular mass. Yeah, so this is the answer without units. Some question asks you what is the molar mass of the gas. So if they ask you for molar mass, then your value will have a unit. In this case, 27.3 grams per mole. Okay, so do take note of what the question asks you to do. I think that will make a lot more sense. Okay, next we are going to discuss exercise 2.4. So for exercise 2.4, we have a sample of m gram of an organic compound vaporized in a gas strange, occupies V cubic centimeters. So again, we need to convert it to cubic meter. So that will be V multiplied by 10 to the power of minus 6 cubic meter. And then the pressure is P bar. So again, we need to convert it to Pascal. So that will be P times 10 to the power of 5 Pascal. Okay. So you're asked what is the relative molecular mass of the compound, the MR. So what we can do over here is we'll just apply the ideal gas equation as before. So we have PV is equals to nRT. So the pressure is P multiplied by 10 to the power of 5 multiplied by volume multiplied by 10 to the power of minus 6 is equals to mass over MR. Do take note that MR is what we want to find eventually, so that's our goal. And then multiply by 8.31, and then multiply by the thermodynamic temperature is in Kelvin already, so T. Okay, so if we shift the equations around, so we'll get MR is equals to, oops, sorry, I shouldn't be writing 8.31 here. I should just be writing it as R, okay, because there's no 8.31 in the answer. So I'm going to get MRT divide by PV. Yeah, so 10 to the power of 5 multiplied by 10 to the power minus 6 is 10 to the power minus 1. So if we shift it around, we take the reciprocal, so that's multiplied by 10 over here. Yeah, and then when you try to compare the answers over here, which we have derived, with any of the answers given in A, B, C, D, right? You'll notice that none of the answer has R. Okay, and then some of the information is missing as well, because for example, you notice that one thing that's peculiar about all the answers is that you have something like 22,700 in all your answers, and then you have 273 over here in all your answers. So that's kind of weird, right? Yeah, so once you have all these in your answers without R, the first thing that should come to your mind is perhaps they don't want to use 8.31. They are you're supposed to re-express R in terms of other variables. So because you already see 273 and 22,700, right? Maybe the STP condition comes to mind. Yeah, because for STP condition, the molar volume is defined as 22.7 dm cube per mole. And then yeah, the rest of the condition, 273 Kelvin especially. Sorry, so with that, then we can just represent R. Maybe we'll try. Okay, so R in this case is equals to PV over NT. Okay, and then you know that in terms of pressure, so that's 10 to the power of 5 Pascal, and then in terms of volume, so that's 22.7 times 10 to the power minus 3. Remember that dm cube you need to convert to cubic meter, so you need to factor in 10 to the power minus 3, and then divide by 1 more, and then 273. Okay, and then if you just simplify it, you will get 10 to the power of 5 times 10 to the power minus 3 is 10 to the power of 2. So that's 2270 divided by 273. Okay, now you notice that if you substitute R into over here, you'll realize that 2270 times 10 is 22,700. Yeah, so you should get 22,700 on top. Okay, and then you should get M, you should get T as well. Yeah, and then of course this is gone, and then PV is below. Okay, and then 273 is below as well. Yeah, so with all this coming into play, the best answer here is therefore option A. Yeah, so option A is the correct answers for this particular exercise. Okay, so in short, next time in your MCQ question, if you do not see a representation of R, and then you do see some familiar numbers like 22,700 or 24,000, then maybe it is time to look at how you can re-express R. Okay, next we'll move on to section 2.4 on combined gas equation. Okay, so I think over here I will just go straight into the examples because there were quite a bit of details involved. Okay, so what exactly is happening here is that they are just trying to combine equations if the number of moles of gaseous molecule is kept a constant, but it might be a little bit confusing for some students. So what I can do here is basically you might want to know that for any particular system, right, because PV is equals to nRT, normally mass is kept a constant. If let's say, I mean, I can just give you a random example. So if in one condition, right, we have a certain pressure, we can call it P1. We have a certain volume, we call it V1. And we can have a certain temperature, we call it T1. So in this case, your ideal gas equation will therefore be P1 V1 is equals to nRO multiplied by T1. Okay, and then if you shift the variables around, the number of moles will therefore be equals to P1 V1 divided by R P1. Okay, then for the same amount of gaseous particles or gaseous molecules, right, what you can do is I can choose to change the variables. Let's say I want to subject the system to a different pressure, different volumes, and different temperature. When you do that, the number of moles of gaseous particles still remains the same. Of course, if the gas particles decompose, then that's a separate issue. Yeah, but if it doesn't decompose, then the number of moles will still stay the same. And because the number of moles still stay the same, in your new condition, right, maybe you change it to a P2, a new pressure P2, a new volume V2, and maybe a new temperature T2. Yeah, you can actually equate both of these equations together. So P1 V1 over T1 is actually equals to P2 V2 over T2 because the R gets cancelled away, so you can cancel the R away. Yeah, so this is what we call combining gas equations together. But you realize that fundamentally you are not exactly combining, but you are just making use of a fundamental principle known as the conservation of mass. Yeah, where n must be a constant. Yeah, so if you can understand that principle, in all honesty, there isn't really a need for you to do the so-called combining the equations together. Yeah, but of course, if you wish to remember this relationship, you can. But as I stress to students very often, there isn't need for you to memorize any relationship, even any of these variables. Like for example, if let's say temperature is kept a constant, you can just cancel away the temperature terms and you get P1 V1 equals to P2 V2. Yeah, so even if you can do that, if you are extremely good in your memory, you want to memorize everything, I don't think you should, because that will only keep unnecessary things in your head lah. Yeah, but of course, if you can, if you wish to, you can do that. Okay, and another thing you might want to take note of is that it is of vital importance for the units to be, again, in their SI units lah. So pressure is in Pascal, volume is in cubic meter, and temperature is in their thermodynamic temperature. Yeah, however, for those of you who are sharp enough, right, you might realize that for pressure and volume, they need not be converted to the SI units. The reason is because the terms gets cancelled off. Okay, so what do I mean? So for example, let's say we have a fixed temperature. So for my fixed temperature, my P1, if I want to convert it, let's say from bars to Pascal. So that will be multiplied by 10 to the power 5, right? And then let's say my volume is in dm cube, for example. So I want to convert my volume to be I want to convert my volume to cubic meter. So I need to multiply this by 10 to the power of minus 3. Okay, so you realize that if the P2 and V2 are also given in bars, which is P2 bar, and also V2 dm cube, right? You notice that the constant in this case, will actually be cancelled off. So 10 to the power 5 will be cancelled off, 10 to the power minus 3 will be cancelled off. Yeah, so if you do take note of this. So for that reason, right, any conversion which involve multiplying by a fixed variable, right, a fixed constant, right, actually you do not need to convert them back to the SI units. Yeah, but temperature you need to, because temperature you are adding 273 to kelvins, you are not multiplying. Okay, so if you can remember this little thing, then yes. If not, then I suggest one good way is just to keep doing conversion, which normally I will probably not suggest students to do it in the rush for exams. Okay, so with that, we can take a quick look at exercise 2.5. Okay, so you were told that an air bubble rises from the bottom of the sea where the temperature is 6 degrees Celsius. So yeah, 6 degrees Celsius. Pressure is 8.5 atmosphere. Okay, so again, temperature definitely must convert. So maybe we can try to do the conversion first. Okay, so we have 6 degrees Celsius, so 6 plus 273. So that will be 279 Kelvin. Okay. Pressure I don't need to convert because I can leave my answers in atmosphere. The surface, water surface has a temperature of 24 degrees Celsius at 1 atmosphere. So again, I need to convert this. So I need to add 273 to 24. So that's 273 plus 24. That will give me 297 Kelvin. So that's 297 Kelvin. Pressure I don't need to convert. Okay, calculate the volume of the bubbles in cubic centimeters. Okay, so the volume of the bubble is kept constant here, cubic centimeters. Okay, if its initial volume is 0.03 cubic centimeters, so everything is in cubic centimeters. So again, in that case, I do not need to convert my volume to cubic meter, and I do not need to convert my pressure to cubic to bars. Okay, so let's see how we can do that. Okay, so initially the temperature is 279 Kelvin. Okay, so I'm just going to do a fraction. So this is 279. Okay, then the pressure is 8.5 atmosphere, so that's 8.4. Okay, the volume is given to be 0.030, so 0.030. Okay, so I'm just going to write this out. Okay, and then at the surface, temperature is 297 Kelvin. Okay, pressure is 1 atmosphere. Okay, it's given over here 1.0. Okay, the volume I don't know. Okay, so one equation, one unknown, so we can easily do that. Okay, so with that, I'm just going to bring 297 over to the other side, and then 1.0 to the bottom. So I'm going to quickly punch my calculators. I'm going to get volume is equals to 0.27 cubic centimeters. Okay, for students who are really afraid of making mistakes, right, if you wish to, you can just convert everything to SI unit. So if let's say 8.4 atmosphere, right, you just need to multiply by 101,325. Then you can just convert this to cubic meter, 10 to the power minus 6. You will realize that they will cancel out. Okay, if you wish to, you can just write them out so that you feel safer. And then eventually these will all be cancelled out. Okay, so you'll still end up with a simplified working. Yeah, but after you become more experienced, then I'm sure you can just skip this. Okay, yeah, we'll look at 2.6 now. So you have a 400 cubic centimeters mixture of petrol vapor and air is taken into the cylinder of a car engine. So again, temperature converts to Kelvin, please. So multiply by, or rather you need to add 273 over here. Okay, so 200 plus 273, so that's 473. That's 473. Okay, Kelvin. A pressure of 100 kPa. The piston compresses this gas mixture to 50 cubic centimeters. Okay. Assume gas do not react. Temperature kept a constant. Okay, so temperature kept a constant. Actually, I don't need to do a conversion because there isn't a need to. Okay. So in this case, we can simply use P1 V1 is equals to P2 V2. Okay. So initially we are looking at 100 kilopascal. So so that is 100 in terms of kilopascal, and then we multiply by 400 cubic centimeters of the petrol vapor. The final pressure we don't know, the final pressure, okay, but we know the final compressed volume, which is 50.0 cubic centimeters. Okay. Please take note, initially cubic centimeters, now also cubic centimeters, so that's fine. Again, if you don't feel safe, you can always do the conversion. What you can do is just multiply this to 10 to the power minus 6, 10 to the power minus 6, and then 10 to the power 3. But you realize that it's not necessary at the end of the day, because they will be cancelled out anyway. Okay, so if you do a quick calculation, you realize that P2 is equals to 800 kilopascal. Okay, I think you can just easily do 50, 100 divided by 50 is 2 times 400 is 800. Okay, so yep, I hope you find the calculation to be not too difficult, because you just need to be very clear-headed what you need to convert and what you do not need to convert. 2.5 graphical representation or graphical relationship tends to be a challenge for students, but maybe I can stress that most of what you need to know over here are stuff which you have already learned in secondary school. Yeah, so basically you need to arrange them to the form y equals to mx plus c, and you need to go through the logic in your mind. Yeah, so I think the best way to do this is to look at examples. So for exercise 2.7, we have situation 1 where we have a fixed amount of gas. Fixed amount also means fixed mass. So so n is fixed, so therefore m fixed as well. You cap it at constant temperature. So you are asked to sketch a graph of PV against P and PV against V. So again, PV is equals to nRT over here. Because I fix n, right? So I'm going to just color code. So what's going to happen is n will be a constant, R is the ideal gas constant, and because I'm fixing temperature, so T is a constant. So regardless of what happens, PV is a constant. Yeah. So if PV is a constant, I'm going to get a horizontal line that is parallel to the x-axis, regardless of what my volume and what my pressure is. Because my volume, if my volume change, right, the pressure term will change accordingly, so that the product of the pressure and the volume will give me a constant value, which is PV. Okay, so if you can come to terms with this logic, then it will not be too difficult for you. Okay. Yeah, then next we look at situation 2, which is an extension of Boyle's law. So we have a fixed mass of gas at 2 different temperature, T2 which is higher than T1, so sketch on the same axis. So again, we'll have PV is equals to nRT. So again, we try to fix the amount of gas at different temperature. So again, what we can do here is we can put P on the left hand side, because P is the so-called y-axis. Okay, so this is actually equals to N R, okay, T, okay, and then multiply by 1 over V. Okay, so again, we'll just highlight the term which are constant. So N is a constant, R is a constant, T over here, I think we need to be explicit. So T2 is greater than T1. So which means numerically, thermodynamic temperature T2 is bigger than T1. Okay. So you know that for Boyle's law, the graph is a curve. Okay, because as volume tends to infinity, pressure tends to 0. As volume tends to 0, pressure tends to infinity. So again, we get a graph that is shaped like this. Okay, so maybe if I sketch it in a nicer way, so the shape will be something like this, just curve all the way down. Okay, so this is not so nice, so let me just sketch it in a nicer way. Okay, yeah. Okay, you shouldn't have the tail at the end, so you just have to be a bit careful when you sketch on paper. Okay, now let's try to see a difference. Okay, so over here, right, what we are going to encounter is that your nRT value, right, will be different. Okay, for different temperature. Okay, so let's say at T2. Okay, so let's say I mean just a random way of looking at it. So if temperature is T2, right? So therefore, I expect nRT2 to be a greater value than nRT1. Okay, so are we expecting this? Okay, so if we are expecting this, then therefore is it right to say that pressure, the P value, will be a higher value than P1 if that say the temperature is T1? Yeah, for a fixed volume. Okay, so let's say I mean we can just look at it simply. Let's say for a fixed volume, let's say I fix my volume here. Okay, so let's say it's a constant value. Let's say I call it V0, for example. Yeah. So if I fix my volume here, right? So therefore, you can see that the pressure will be directly proportional to the temperature. So therefore, at a higher temperature, my P2 will be somewhere here. Yeah. So if I'm going to sketch a graph, then it will look something like this. Right, so at every point it will be higher, so it should be parallel, but I think I didn't sketch it out very nicely. Yeah, so it should look something like this. Yeah, so therefore with that, then T2 will be higher, and then T1 will be lower. Yeah, you can always discuss the logic, go through the logic in your mind if you wish to. If not, then you can always plug in some numbers if you wished. Yeah, but just make sure that your logical thinking is you need to be very logical when you think which scenario corresponds to which. Yeah, because if you are confused, and let's say if it's reciprocal relationship, sometimes you will get you will make mistake or unknowing mistake. Yeah, so sometimes beginning students, we tend to advise them to maybe just pluck out some values, or maybe keep some values as a constant, and then you see how it varies. Okay, so in short, what I can share with you is that in order to sketch out the graph properly or nicely, or interpret them correctly, you just need to be very strong at understanding how to sketch graph involving y equals to mx plus c, and then looking for constant values. So it's all secondary school knowledge, but I think it does couple in with some interpreting skills on your end when you're dealing with H2. Okay, then okay, so let's say for this case, which temperature is higher, T1 or T2? So again, you are plotting pressure directly against volume. Okay, so with this, you have PV is equals to nRT. Yeah, and then P is equals to nRT, and then 1 OV. So if you plot P directly against 1 OV, you get a straight line which passes through the origin. Yeah, so therefore your nRT will be the gradients of the line. So right, so this will be the gradients. Yeah, so if this is the gradients, definitely T2 is higher than T1. Yeah, because thermodynamic temperature can only take on a value above 0. So if it's a greater value, that means that numerically it's larger in terms of magnitude. Yeah, then therefore the gradient is steeper. So T2 greater than T1. So this is of course of a higher temperature. Yeah, so this is the logic which you need to go through in your mind. Yeah, so with the same idea for exercise 2.8a, right? So you're asked which pressure is higher, P1 or P2. So again, same thing. So PV is equals to nRT. Yeah, so we are plotting V against temperature. So therefore V is equals to N R over P and then T. So against V against thermodynamic temperature is a straight line which passes through the origin. Yeah. So in that case, if let's say, right, P2 is a greater number than P1. Okay, so let's say P2 is a larger number than P1. Okay, then I will expect the graph for P2 to take on a smaller gradient. Am I right to say that? Because P is found at the denominator. Yeah, so therefore the smaller the P value, the greater the gradient. Okay, so in this case, because P1 gradient is more gentle than P2, so therefore I can conclude that P1 is of a greater value than P2 in terms of pressure. Yeah, and of course pressure can only be positive. So my initial assumption is not correct. Yeah, would that be okay? I think you need to think through it on your own, especially when P is found as the denominator. Okay, then with the same logic, which temperature is higher, T1 or T2? So again, PV is equals to nRT. Yeah, so again, PV is a constant. Yeah, but a constant can also take on larger values depending on T, right? Yeah, so if the T1 line is always above the T2 line, so therefore T1 must be of a greater thermodynamic temperature as compared to T2. So that is always found above. Yeah, so therefore T1 is a higher temperature, is of a higher temperature. Okay, then very quickly we look at exercise 2.9. So you're asked which graph correctly describes the behavior of a fixed mass of an ideal gas. So again, there's a thing that is kept constant. You have a fixed mass. Yeah, so there are a few ways to do this kind of question. Either you plot the graph directly, and then you see which corresponds to which, or you can just look at the plot and then go through the ideas in your mind if you are very sharp. Okay, so what we can do is let's try to do both. So again, we make use of PV equals to nRT. So PV is equals to nRT. Okay, so therefore PV over T is actually equals to a constant. Yeah, so therefore this graph is correct, because equals to a constant means that I get a straight line that I get a horizontal line that is parallel to the x-axis. Okay, then again PV equals to nRT. So we fix the mass. So we fix N, R is fixed, T is also fixed because we are told that it's fixed. So therefore I expect the graph to be a horizontal line that is parallel to x-axis. So again, this graph is incorrect. Okay, so for C, same logic. If I have PVT, I plot it against V, right? Because PVOT is a constant. Again, I expect a horizontal line that is parallel to the x-axis. So what I'm given here is incorrect. Okay, and this is a very tricky option, because you know that at constant T, right, PV equals nRT. So again, at constant T, N is fixed, R is fixed, T is fixed. So PV is a constant. So PV equals to a constant, right? Yeah. So you'll be thinking horizontal line parallel to the x-axis, right? But the axis actually reverses. Yeah, so PV is actually on the x-axis now. So the correct graph should be like this. Yeah, so therefore whatever that's given is incorrect. So the only correct option is A. Okay, so it's quite tricky. So do open up your eyes a bit when you are doing questions like this. Yeah, so sometimes they will try to trick you. Okay, so very quickly, we are at the third section, learning objective 3D using Dalton's law. So there's this Dalton's law of partial pressure which you need to be familiar with. So I think it's mentioned that the partial pressure or exerted by a particular gas is known as the partial pressure. So that is the pressure exerted by the particular gas in the system. So the total pressure of the gases in the system is the sum of the partial pressure exerted by each of the gases. Okay, so if you are using the ideal gas equation, you can actually express each of these pressure exerted by the individual gases in terms of its ideal gas, using the ideal gas equation. So therefore you can shift around. So because PV is equals to nRT, so therefore P is equals to nRT over V. Yeah, so with nRT over V, you get something like what is given here, and then you realize that you can take out your RT over V term. Okay, so eventually you get N total, so that's the P total. Okay, so I think that's not very inspiring, but that's something which you can convert and you can make use of. And then from here, right, they actually come up with a new term. So for each of the gases, if you divide the number of moles by the total amount, you get what we call expressing it in terms of partial pressure. So that means that if I multiply, let's say if I want to find out the partial pressure of PA, right? So essentially that's just amounts of A present divided by the total amount multiplied by the total pressure. So this factor, number of moles of A divided by the total number of moles, we call it mole fraction. Yeah, so this is a new variable which you need to be familiar with, which is the mole fraction, and I believe this is not taught to you anywhere in secondary school, unless you have been exposed to some of it earlier. Okay. Yep. So with that, we'll try to work on exercise 3.1. So you have 2 moles of oxygen and 1 mole of nitrogen in a container with a volume 10 dm cube, 298 Kelvin. You are asked what is the total pressure, and of course, what is the partial pressure of oxygen. Okay, so that's pretty straightforward. Basically, the total number of moles is 3. Okay, so you have 3 moles in total, and then so we need to just write this out. So total number of moles is 3. Okay, so if you use PV is equals to nRT, then you know that the P is actually equals to 3 times 8.31 times 298 divided by the volume, which is 10 dm cube. But this is in dm cube, so you need to convert to cubic meter, and then you can very quickly get 7.43 kilopascal. Okay, so that is the total pressure. Okay, then you notice that I have 2 moles of oxygen and 1 mole of nitrogen. Yeah, so therefore the partial pressure of oxygen is simply the number of moles of oxygen, which is 2, divided by the total number of moles, which is 3, multiplied by the total pressure, which is 743 Kelvin. Okay, so from here you can easily get 495 kilopascal for the partial pressure of oxygen. Okay, yep. Then for 3.2, you have a flask Q contains 1.00 dm cube of helium at a pressure 2 kilopascal. Then you have R contains 2 dm cube of neon, pressure of 3 kilopascal. So if the 2 flasks are connected with a constant temperature, what is the final pressure? Okay, so again, there are really a lot of ways to do a question like this. So it can be a fast way, or it can be a slow way. So depending on how you want to go about doing it. Okay, so what you can do is, first you need to know that the total number of moles, okay, is made up of the total number of moles of helium and the total number of moles of neon. Yeah. So this is something which you need to know right at the start. Yeah, so total number of moles of gaseous particles in flask Q and R is the total number of moles of helium and neon combined. Obviously, right? Yeah, because at the end of the day, I want to know the final pressure of the system. Yeah, so I need to know this from the start. And then now I need to re-express the N in terms of PV equals to nRT. Yeah, so because PV equals to nRT, so therefore N is PV over RT. Okay, so from here, I will be able to get P total, V total, divided by T total, and R, equals to P helium, V helium, over R, and T helium, plus P neon, V neon, over R, and T neon. Okay, now, very, very interestingly, and very, very quickly, right? The question actually made our life easier lah. The temperature is the same. Okay, so therefore RT can be cancelled. Temperature is the same means that final temperature and before is the same. So therefore we don't need to care. So we cancel them. So the whole relationship is now simplified to PTVT equals to P helium V helium plus P neon V neon. Okay. Now the total pressure is what we want to calculate. The total volume, can we determine that easily? Yes, we can, right? It's just 1 plus 3, right? So, I'm sorry, 1 plus 2, right? So that's 3.00. Do we need to convert to cubic meter? We don't have to because it will be cancelled out, okay? Equals to, pressure of helium is 2.00. Okay, the volume is 1.00. Pressure of neon is 3.00. The volume is 2.00. Again, I don't have to convert because it will cancel out. Okay, and then from here, we can get the total pressure is actually 2.67 kilopascal. Okay, so I hope this is not too daunting and it's not too difficult to work on. Yeah, so again, you need to get the logic correct. And again, this is not the only way to do it. If you choose to memorize some formula, like some students have to memorize PTVT divided by final temperature is equals to P1 V1 over T1 plus P2 V2 over T1. All this, it's fine, but you really do not need to, as long as your logical thought process is strong. So again, I normally will advise students to understand the fundamentals of working on the problems rather than to memorize formulas. Yes, so it's only when you understand how to work through these problems that you realize you do not need to memorize any formulas. Okay, all right. We have exercise 3.3. So a 12.5 dm cube scuba diving tank is filled with a heliox mixture. So you have 24.2 grams of helium, 4.32 grams of oxygen at 298 Kelvin. You are asked to calculate the total pressure and the partial pressure of helium and oxygen in the mixture. So again, are you given a temperature? You are not given a temperature. Assume room temperature. Okay, in this case. Okay, so let's try to. Oh, sorry. What am I talking about? You are given a temperature, 298 Kelvin. Okay, so the first thing we need to do is calculate the number of moles of helium, which essentially is 24.2 divided by 4. So you get 6.05 moles. Then after that, calculate the number of moles of oxygen gas. So it's 4.32 divided by 32. Okay, so you get 0.135 moles. Okay, then I'm sure the rest isn't something which is too difficult, because all you need to do is to sum these two up. Okay, so 6.05 plus 0.135, you get 6.185. So N total is equals to 6.185 moles. Yeah, so the total pressure, so we'll try to calculate the total pressure first. So total pressure, yeah, is equals to 6.185 multiplied by 8.31 multiplied by the thermodynamic temperature 298. Okay, divide by the volume, which is 12.5 dm cube. Okay, so if you do a quick calculation, punch your calculators, you should be able to get 1.23 times 10 to the power 6 Pascal. Okay, then in order for you to calculate the partial pressure of helium and oxygen, so that's straightforward, because the partial pressure of helium is simply the amount of helium divided by the total amount, which is 6.185, multiplied by the total pressure, which is 1.23 times 10 to the power 6. Okay, so from here you will very quickly get 1.20 times 10 to the power 6 Pascal. Okay, to calculate the partial pressure of oxygen, you can either just take the difference between this and this, or you can do the same working. Use the same variable, which is 0.135 divided by 6.185 times 1.23 times 10 to the power 6. Okay, so you should be able to get 2.67 times 10 to the power 4 Pascal. Okay, some of the students will ask, in our intermediate steps, how many SF should we leave our answers to? Okay, so it really depends, because your total pressure is not really an intermediate step, because you're asked to do that. Yeah, but of course, when you plug the values in here, right, you should be introducing at least one more significant figure. So if I do a quick recap, let me try to punch, and then I just want to see the numbers. You should be getting so over here, the numbers you should be using will be 1.2253, yeah, times 10 to the power 6. Yeah, so if you are using these numbers, then I think it makes more sense for you to get the final answer to be close to what I have input here. Okay, so I think all these are relatively important things you need to take note of when you perform calculation, especially let's say the question asks you to calculate the total pressure as an intermediate step, but you should leave your answer to 3 SF, at most 4. But when you need that value and you use it in your final 2 calculation, right, you should actually use one more significant figures. Okay, yeah. Then we have section 4, which is a very important learning objectives in quite a lot of exams, because this is a very popular recall kind of questions that they will ask. Yeah, so it's related to the assumption of ideal gas, and it is actually based on the kinetic particle theory. So there are 3 assumptions which you need to know. So the first assumption is that because the gas particles has almost negligible size, yeah, so we normally say that the total gas particles, right, so the sum of all the gas particles, their total volume is actually negligible as compared to the volume of the container. Yeah, so this is a quite a popular assumption which you need to be aware of. Okay, and following straight up will be intermolecular forces of attractions are actually negligible. Yeah, as compared to those of the real gas. So in that sense, you do assume that from what you learn in chemical bonding, all the forces of attractions, whether are they dispersion forces, are they permanent dipole interaction, or hydrogen bonding, all this, they are non-existent. Okay, so yeah, so something which you need to know about the assumption for ideal gas laws. Okay, so a very common mistakes students make is they will tend to say that the gas occupies like negligible volumes. Yeah, take note that the gas occupies the volume of the container. Here we are talking about the gas particles. We are not talking about the gas. Okay, so any gases occupies the volume of the container. Yeah, but we are talking about the size. Okay, I mean the volume of the gas particles in total. Okay, is negligible as compared to the volume of the container. Yeah, so there's a bit of a difference. Yeah, so normally for A-level question, they will tend to ask for only 2 assumptions. Yeah, but some questions they do ask for 3. So if they do ask for 3, the third assumption would be a perfect elastic collision between gas particles. Okay, so remember this, perfect elastic collision, which means no energy is lost in the process. Okay, yeah, I think we have an exam tip here. So if you're asked to write 2 assumptions, so you should write the first 2. Yeah, if you're asked to write 3, then you can include the third one. Okay, so for exercise 4.1, you were told that argon exists in the atmosphere as a monoatomic inert gas. So you are supposed to use the data booklet to calculate the volume of an argon atom, indicate the units clearly. You are told that the volume of a sphere is 4/3 pi r cube. Yeah, so again, to use the data booklet, so all you need to do is to go to the relevant information. So it's actually found a few pages later, so I think it's found here. Okay, so argon's radius, okay, the units is actually nanometers. So the argon van der Waals radius is 0.190 nanometers. Okay, so 0.190. Yeah, so 4/3 pi r cube. So therefore the volume of argon atom is actually equals to 4/3 pi multiplied by 0.190 times 10 to the power minus 9 nanometers. We need to convert to cubic meter cube. Okay, so if you punch your calculator, you should be able to get 2.87 times 10 to the power of minus 29 cubic meter. So that's a really small volume. Then they ask you to calculate the total combined volume of 1 mole of argon atoms. So the total combined volume basically is just this number multiplied by the Avogadro's number. Yeah, so the total volume of 1 mole of argon, so it's 2.87 times 10 to the power minus 29. 2.87, okay, multiplied by 6.02 times 10 to the power of 23. Okay, so you should be able to get 1.73 times 10 to the power of minus 5 cubic meter. Yeah, so if the gas volume of 1 mole of argon is 24 dm cube, calculate the percentage of total volume occupied by the argon atoms themselves. So basically, you will take this number, divide by 24 dm cube, but you can't take it directly because you need to convert 24 dm cube to cubic meter. Okay, so therefore for part C, your calculation would then be 1.73 times 10 to the power minus 5 divided by 24.0 multiplied by 10 to the power minus 3 multiplied by 100%. So you will be getting 0.0721%. So this is like a miserable percentage. Yeah, so therefore our ideal gas assumption is quite valid. Okay, so yes, so it's actually justifiable. Relevant assumptions will be gas particles occupies negligible volume as compared to the volume of the container. Okay, then next we have 4.1, which states the conditions for real gas to behave ideally. So there are two important conditions here which you need to be aware of. So it's low pressure at high temperature. Okay, the reason why low pressure is put in as one of the conditions is really because at low pressure the gas particles tends to be far apart. So because of that, because they are far apart, and you probably don't have a lot of particles as well. So number one, their intermolecular force of attraction can be negligible because they are far apart. And then number two is because there are much fewer gas particles at low pressure as compared to high pressure, right? So the total volume being negligible of the gas particles being negligible as compared to the volume of container is more valid. Yeah, so because of that, you expect for real gases, if they are at low pressure, their behavior will tend to approach ideal gas. At high temperature, I think this is obvious, because at high temperature, the gas particles will have enough energy to overcome the forces of attractions between the particles. Yeah, so the kind of energy we are talking about here is actually kinetic energy. Okay, and because they have enough energy to overcome the intermolecular forces of attractions, we will consider the intermolecular forces of attractions to be negligible. Okay, so with that, behavior of real gas approach ideality at high temperature. Okay, then our next section will be 5, where we are looking at how real gas, about real gases and how they deviate from ideal behavior. In 5.1, we are going to explain the deviations at high pressures. Okay, so imagine from this particular drawing that if I have a piston here with a certain number of moles of gaseous particles, if I'm going to push it down, meaning that I'm going to increase the pressure, you will notice that the total volume occupied by the gas particles, right, is reduced drastically. So in that case, the total volume occupied by the gas particles, right, may be significant as compared to the volume of the container as compared to when it's at low pressure. So because of that, it might deviate relatively significantly from ideal behavior. And then at the same time, because the gas particles are very close to each other, they may experience significant intermolecular forces of attractions, because intermolecular forces of attractions is distance dependent. So the closer they are with each other, the stronger will be the intermolecular forces of attractions. Okay, so we have a drawing here, or rather we have a graph here showcasing the behavior of some real gases as compared to ideal gas. Ideal gas is always this horizontal line that is parallel to the x-axis. I hope you can understand why, because PV is equals to nRT. Yeah, so for a fixed temperature, so normally we will measure the behavior at a fixed temperature, so in that case 300 Kelvin, and we are normally looking at a fixed number of moles of ideal gas as well. So N is fixed. So in that case, PV is equals to nRT, which is equals to a constant value. So when it's a constant value, you are expecting a horizontal line parallel to the x-axis. Yeah. Then because of that, ideal gas, we will always use the ideal gas line as a reference as to when we plot the real gas behavior, we will be able to see how far it deviates from ideality. So in this case, if you look at nitrogen over here, right, yeah, you realize that nitrogen just sort of tuck in a little bit, and then after that it slowly goes beyond a certain point. So we call any part of the graph below the ideal gas line negative deviations. Yeah, so this is negative deviation. Anything above, we call it positive deviations. Yeah, so for CO2, for this portion below is negative deviation, and then after that, you expect the graph to continue upwards. Okay, so when it continue upwards, this will be a positive deviation. Normally for H2 chem, we are a little bit more concerned, or we are more concerned with negative deviation rather than positive deviation. So with that, you can sort of be assured that normally the questions will focus more on asking you about why the real gas part of the graph, or why for the graph for real gases, they tend to be found below the ideal gas line, beyond or beyond a certain pressure, for example. Okay, so I think one thing you can take note of from this graph is that CO2 deviates more from ideality as compared to nitrogen gas. This will not come as a surprise, because number one, the molecular size of CO2 is bigger than N2, and then number two, right, the dispersion forces, or the instantaneous dipole-induced dipole interaction between CO2 molecules is significantly stronger than that between N2 molecules. So this greater deviation from ideal behavior, it's not surprised. It's not surprising. Okay, and another common misconception student might have is that this particular point when they cut the ideal gas line, right, does it mean that they behave ideally? So the answer is no, it doesn't mean that they behave ideally. So we don't compare the crossing points. So this graph is being obtained, right, when we try to determine the pressure at various points, or rather determine the value of PV at various pressures. So on the whole, this is the graph we are getting. So when we get the graph and we plot it, it looks like this. So it doesn't mean that when it crosses the ideal gas line, that means that it's behaving ideally. So that is the number one common misconception students will have. Okay, and then how can we understand the negative deviation? I think later on in the notes, part of it is being explained to you. Okay, so maybe we can just dive straight into that. So for 5.2, explaining deviation at low temperature. So over here, do take note that the temperature is 300 Kelvin. Okay, so it's only one temperature. And for section 5.1, right, we are not exactly explaining a lot of things. So we are just showing you an example of a deviation from ideal gas behavior at high temperature. So this tends to be what we call a positive deviation. Yeah, and we are fixing it at one temperature, which is 300 Kelvin. The detailed explanation will be explained to you later on. So in this case, for section 5.2, explaining deviation at low temperature. So you notice that, let's say for a gas such as nitrogen, right, the lower the temperature is, it deviates more and more from ideal gas behavior. Okay, of course, you have to assume that it hasn't liquefied, or it hasn't turned into solids, obviously, right? So I think we can understand why as well, because as the temperature lowers, right, the particles have less kinetic energy, so they move less readily. And because they move slowly, right, the probability of them being close to one another is greater. Okay, and in that case, I think it's written here as well, they do not have enough energy to overcome the intermolecular forces of attractions. So intermolecular force of attraction increases in strength drastically. And you realize that the behavior is not exactly linear, so it's very difficult for you to predict. Yeah, so it's almost impossible for you to predict how it will behave. Yeah, so it's not like it's like this and then like this, like this, like this, or like this. Yeah, so it becomes sharper and sharper as the temperature lowers. So your job is not really to predict how it will be like accurately, but rather to know or to understand whether is it likely to be a positive or negative deviations. Yeah, so you notice that when we sketch the graph, we didn't continue beyond that. Yeah, so if we continue beyond that, so you expect the thing to actually increase. Yeah, so that is something you might want to be familiar with as well. Okay, so one gas might deviate more than the other gas at the same temperature and pressure, and we have illustrated this earlier on as well. That is because CO2 forms stronger intermolecular force of attraction, in this case dispersion forces or instantaneous dipole-induced dipole interaction. So if we introduce a gas such as ammonia, which forms strong hydrogen bonding between molecules, so you expect it to deviate even more from, say, CO2 or maybe methane. Okay, really depends. And then I think earlier on we sort of mentioned this a little bit as well. So there is both positive and negative deviation. Okay, so a negative deviation, we tend to explain it by focusing on the intermolecular forces of attraction. Okay, yeah, because of the stronger intermolecular forces of attraction, so the volume observed, okay, so the observed volume for real gas, right, is actually smaller than expected. So you can visualize it such that at every point over here, right, if it's an ideal gas at a fixed pressure, right, so it will still be PV, the value of PV. However, the volume, the real volume, actually reduces quite drastically because of the significant intermolecular force attractions, and that is the deviation we're talking about. And this is due to the attractive forces which brings the particles closer to each other. Okay, what about at higher pressure? How come at higher pressure suddenly the real volume become bigger than ideal gas volume? Okay, so you can also view it as at higher pressure, right? Because they are compressed to a very huge extent. So now repulsive interaction dominates. Repulsive interaction meaning, right? So for example, okay, I think we can imagine it to be this way. So let's say you are in a room and then you are here. Okay, so when the volume of the room decreases, right, actually you are not exactly affected that much, but maybe you feel a bit claustrophobic, and then maybe you just stay at one corner more, etc. But you will not tend to force yourself out, because the volume is still the volume of the space, the air space, is still quite relatively significant. But if I'm going to force the volume until like it just holds you like that, right, then now you are not going to do any. You are definitely going to do something, right? You are just going to push yourself against the wall. Okay, in that case, you try to make it bigger than it should be. So that is what we call the repulsive interaction now is at play. So some of the introductory textbook actually went on to actually say that over here at this region, this is attractive interaction, and then beyond that is repulsive interaction at play. But again, for H2, we don't really focus a lot about it. So that's why we did not actually go into details in the notes. Okay, but what is more important is for you to recognize that for negative deviation, the value of PV is below the ideal gas, positive deviation is above, and roughly you are able to sketch out the shape of the graph in this manner, and then that will be good. And then so let's say if this is 300 Kelvin, so let's say at a lower temperature, let's say 250 Kelvin, something like that. Okay, so if you are able to sketch a graph which looks something like this, I think that is a lot better lah. That is good enough, in fact. Okay, then moving on to exercise 5.1, interpreting real gas behavior from a plot of PV over RT against P. So again, ideal gas line is over here. Okay, so you are given the following curves represent behavior of equal amounts. Equal amount is important as well, because so that you are comparing apples with apples and not apples with oranges. Okay, of 3 real gases and an ideal gas at fixed temperature. Ideal gas is, we don't have to mention which is the ideal gas because it will be the horizontal line. Amongst the options given, what could the possible identities of the 3 gases be? So from here, very straightforward. The one which deviates the most will have the strongest intermolecular forces of attractions. Okay, so in that case, Z deviates the most. So definitely amongst everything else, I should be choosing ammonia, because between ammonia, hydrogen gas, and nitrogen, right, ammonia forms the strongest intermolecular force of attractions. Okay, then of course Y deviates by a bit, so definitely Y must be nitrogen gas, because nitrogen gas forms stronger dispersion forces between molecules as compared to hydrogen gas. So therefore the option is D. Okay, and do take note that hydrogen gas is one of the rare few, right, where the line, most parts of the line is actually above the ideal gas line. So if you look up online resources, this is what you will notice. Okay, moving on to exercise 5.2, right? So we have the value of PV plotted against P for 2 gases, and then ideal gas and a non-ideal gas. So where P is the pressure and V is the volume of the gases. So again, it's quite standard. Okay, so ideal gas definitely deviates. Sorry, non-ideal gas definitely deviates. Ideal gas will be horizontal and parallel to the x-axis. So question asks you which gas shows the greatest deviation for ideality. Again, it's straightforward. You choose the one with the strongest intermolecular forces of attractions. So amongst all here, all the gases here have dispersion forces or instantaneous dipole-induced dipole interaction between the molecules except for ammonia. So I'll choose ammonia. Okay, next we'll move on to section 6, which is on the distribution of molecular speeds. Okay, so you might want to take note that the average kinetic energy of the gas particles is directly proportional to the absolute temperature. Yeah, okay, so for a particular temperature, all types of gaseous particles have the same average kinetic energy. Yeah, so over here we have different gases. So oxygen is quite narrow, so I think this temperature is a given T, followed by hydrogen H2O, and then nitrogen H2O. You realize that hydrogen has the greatest distribution, and you notice that this is actually sort of linked to the relative molecular mass as well. Okay, yeah, so what is probably more important is actually figure 9, because you will encounter figure 9 a lot more often. So for a gas sample of different temperature, the speed distribution, okay, is shown. So it will peak, so it's like a chi-squared curve, so it will peak at a certain molecular speed, and then after it will taper off towards the end of high molecular speeds. Yeah, so the above is also known as the Maxwell-Boltzmann distribution curve. And for Maxwell-Boltzmann distribution curve, this portion is usually called kinetic energy. Yeah, so it gives you, it shows you the statistical distribution of kinetic energy of the gaseous molecules at a fixed temperature. Yeah, so as I increase the temperature from, let's say, 300 to 500 Kelvin, right, you notice that the Maxwell-Boltzmann distribution curve actually broadens. So that means that there will be a greater proportion of gaseous molecules or particles, right, being able to access a greater kinetic energy. If you're interested, you can read more about Maxwell-Boltzmann's work in this, but their work is of high significance because normally people will think that at a fixed temperature, the kinetic energy of gaseous particles or molecules is fixed. Yeah. However, right, this is far from the truth. It's actually a statistical distribution over a huge range. Yeah, so you will get some particles almost not moving. Quite a number of particles have average speeds, and then very few particles have very high kinetic energy. And then after that, the rest is a distribution. But as I increase the temperature, yeah, the proportion of particles having, let's say, kinetic energy above a certain value, so let's say above this value, actually increases from the part shaded in green to the part shaded in purple. Yeah, so this has strong implication later on in chemical kinetics, where you will learn about activation energy. Yeah, so how the increase in temperature, right, will ensure that a greater proportion of particles having kinetic energy above the activation energy. So that will mean that it will lead to a higher probability of an effective collision. Yeah, so you will learn that in kinetics later on. Okay. So you might want to read through this if you wish to. I think the main thing is the proportion of the area under the graph represents the total number of particles. So that means that whether is it at 300 Kelvin, 500 Kelvin, or even let's say 1000 Kelvin, let's say 1000 Kelvin, right? The area under the graph is the same. Yeah. So inevitably, as you increase the temperature, the peak will decrease, because for the area to be the same, the peak must decrease as the temperature gets higher. Yeah. Okay, so do read through some of these points and be familiar. You will encounter more of them in kinetics, so I assure you that in chemical kinetics, you will learn Maxwell-Boltzmann distribution curve in a more complete and holistic way. Okay, so looking forward, we are going to make use of our understanding of calculating partial pressures in chemical equilibrium, as well as some of the ideas on mole concept in our calculation when we are approaching topic 4 on stoichio. For planning, it might be important for you to understand this idea called gas collection. You will have work on it or encounter it in your laboratory work in one of the lab experiments. Okay, so normally involve collecting gases. So the collection of gases can be gases such as hydrogen gas, carbon dioxide, and then oxygen gas from decomposition of H2O2, and then you oxidize H2O2 by an oxidizing agent, you get oxygen gas as well, and then or decomposition of solids, CO2. Yeah. Sometimes decomposition of nitrates can also give you NO2. Yeah, but that can be quite dangerous. So usually we don't encourage the students to work on this experiment. Maybe for planning is possible. Okay, then I guess you just have to read through. But just one little thing you might want to take note of is that if you really need to collect your gas, make sure you indicate to the examiner that you are using a graduated gas stream, because if your gas stream is not graduated, right, then we don't know how are you going to read off the volume of the gases. Okay, yeah, so that's important. And there is another important idea which is what we call downward displacement. So downward displacement means that you either invert a burette or a measuring cylinder downwards over water, so that you collect over water as the gas bubble through. But just make sure that when you connect your container, when you draw your setup, right, make sure that the tube is really found right below. Okay, sorry, I just need to erase this. Okay, so your tube is really found right below. Yeah, your tube cannot be anywhere else, because if not, then the bubbles will just reach the surface of the water and then get lost into the atmosphere. Yeah, so make sure that you bubble into the measuring cylinder. Okay, if you want to do a dry delivery or dry collection, that is what is shown in A, right? So this is where you use a gas syringe. Yeah, so normally you do a dry collection when, let's say, the gases, right, will react with water, such as NO2, because NO2 actually dissolves in water quite significantly. Yeah, so any gas which don't really dissolve in water, such as hydrogen gas or oxygen gas, downward displacement of water is actually preferred lah. Yeah. Okay, then the final page shows you the generic procedure. I wouldn't say you need to memorize, but I would say read through it and take note of some of the ideas. And especially, I mean, similar to titration, before you collect your gases, make sure you read off the initial reading of your gas syringe and make sure it's a graduated gas syringe. Then after collection, read off the final volume as well. Sorry, not final volume, final reading as well. Okay, so even if you are doing a downward displacement, you should also be reading the initial reading. It can be a burette reading or it can be a measuring cylinder reading, but just make sure that you indicate that. Okay, what else should I be talking about? Okay, over here you might also want to take note that let's say you are using okay, so let's say section B. Okay, so section B over here, where you are using a dropping funnel. Okay, you should also take note of the volume of the displaced air. So some of this part I think you need to be familiar with as well. Yeah, and make sure you do accounts for them when you do the necessary subtractions. Okay, so yeah, gas collection, you would expect to work on it in the lab at least once, and then after you are done with it, you will be more familiar with it. But make sure that when you set up the apparatus, especially for downward displacement, either using measuring cylinder or burettes, you do connect the setup properly, because if you don't connect it properly, then when the reaction proceeds, this particular tube might actually be loosened, and then after that it might come out of the measuring cylinder, and then you need to restart your experiments again. Okay, so with that, we have come to the end of gaseous states, and yeah, do expect more videos on future topics to be up.